Hey guys, welcome back. This is the second lesson in our unit on plate tectonics. It may be the first lesson for some of you, but let's talk about plate movement. Before we get started on talking about why plates move, we need to talk about what makes up the Earth. So the Earth is divided into three main layers. First is the core, all right, that's the inner solid and the outer molten rock. Then we have the mantle. This is the middle layer that is divided into upper and lower mantle, and then the crust, which is the outermost layer, and this is the layer that we live on. All right, so here we see inner core, outer core, mantle, and crust in this lovely image. All right, so you're going to hear the term lithosphere, and the lithosphere is the upper mantle and crust, and it is the area where we witness changes that affect us on our planet right here. This lovely slice that we see here is not to scale, but it shows you the solid core, the liquid core, the mantle. The asthenosphere is part of the mantle and just below the lithosphere, and then our lithosphere, which is the uppermost solid mantle, and the crust. So why are plates moving? Okay, so our plates, so what layer are the plates in? Which layer do the plates float or move on? And how do you think the moving plates affect the layers above them? So thinking about what layer those plates are in, how do they float, how do they move? All right, we've thought about this idea for a really long time, but it's no longer a question. We've actually measured rates, directions, and everything that are happening. So let's see what's... All right, so the main force of movement is called mantle convection. This is still, somewhat of an unanswered question because we can't actually measure it. So the best hypothesis we have is mantle convection. So we believe that things that move towards the center of the Earth get heated up and they rise and move up into areas like ridges or rift valleys, and then cool around the Earth's continental crust and go back and sink back down. All right, and these currents are causing a movement of the plates. All right, so what does convection mean? Convection is really the transfer of thermal energy by movement of heated matter. Convection, you could think about convection ovens. They work by moving heated air with a fan. All right. We also know that warm air rises, or warm things rise, and cool sinks. This creates a current. All right, and we believe that these currents are driving that plate movement. All right, and these are set in motion by subducting slabs that cause the plates to move. All right, so we also witness what's called ridge push. All right, so on an ocean ridge, all right, forces in the Earth push the mantle to rise, to make the asthenosphere rise. All right. And then the weight of the ridge pushes an oceanic plate towards the trench, all right, into a subduction zone. So what does that look like? So if we look at this lovely image here on the side, we have a convection heat in the middle of the ocean pushing up and creating new crust, which we learned about when talking about seafloor spreading. All right, that force then pushes the plate out, all right, and it pushes it until it reaches a trench towards the continental crust, where it then subducts back down into the Earth because it's cool, and then it ends up melting and then becoming magma again, and then part of the mantle, and then it goes through the process again. And this is called ridge push. All right. Now, we have ridge push coming from the center of the ocean. We also have gravity pull. We know we've learned a lot about gravity so far this year. We know that gravity pulls towards the center of the Earth. All right. So we have the weight of the subducting plate, the plate that's being pushed under, helps pull the trailing lithosphere. So it helps pull the next piece down through its weight. So if we look at the image, this part where we have the arrows going down, the slab pull is the shear weight of the subducting plate keeps pulling the rest of it behind it. This is like dragging a piece of string or a piece of paper down. All right, you pull just one edge and the rest keeps coming with it. All right, so continental drifting. You've probably heard of this, Pangea. So the Earth's surface has been relatively unchanged, okay? Is relatively unchanged during the course of an average human lifetime. But however, it has been changing a lot, all right, over the lifetime of the Earth itself. So we know that South America is moving away from Africa at about 2 to 3 centimeters per year. And the islands of Hawaii are moving northwest at 8 to 9 centimeters a year. And then Mount Everest, Earth's highest point, continues to rise. We also know that the valleys surrounding Everest are rising at an even faster rate than Everest is rising, but they're still rising. So who really figured this out? So Alfred Wegener, he proposed the scientific hypothesis about continental movement, and what he did is he essentially looked at the Earth as a puzzle, and he believed that Earth's continents were once joined as a single landmass, and he called this Pangea. All right, so let's ask this question. Who proposed the theory? And he supported this theory using fossil and rock evidence from matching coastlines and by lining up the shapes. All right, and that would be Wegener. So he saw that there were animals in the fossil records on this little piece of South Africa that were also, or in South America, that were also on in Africa. So he proposed that at one point those two places used to touch. All right, boundaries and Earth's feature. So we believe that Pangea began to break apart about 200 million years ago. And then when it began to break apart, large geologic structures, mountain ranges, oceans, would fractured and changed as things moved around. When continents together, mountain ranges, oceans formed. And we see that with things like the Appalachian Mountains, the Himalayan Mountains. All those things are things that we're seeing from things coming together and then oceans forming where things came apart.